When we think about what makes massive, powerful machines fail, we usually picture something big, right? A huge crack, a snapped belt. But what if the biggest threat, the one thing that could bring it all crashing down, was completely invisible? We're talking about a world of microscopic engineering, where the tiniest flaws can have absolutely catastrophic consequences.
I mean, just think about that for a second. It sounds like something out of a movie, but it's a very real problem. A single bubble of gas trapped inside solid steel could be the starting point for a total failure in a machine that weighs tons. So the real question is, how on earth do you even begin to find something like that?
Well, our story really starts with the biggest, toughest machines out there, the kind of heavy equipment that literally builds our world and feeds our planet. The strength of these incredible machines often boils down to one single critical thing: the weld, the exact spot where two pieces of metal become one.
Welding is without a doubt the backbone of heavy industry. It's what holds everything together. And for equipment that has to deal with brutal conditions, constant vibration, wind, rain, the quality of those welds is everything. It's the difference between a machine that runs for decades and one that fails when you least expect it.
So let's meet the villain of our story: pores. It's a simple name for a big problem. See, when you melt metal to weld it, tiny bubbles of gas can get trapped as it cools down and solidifies. What you're left with is a microscopic hole, a little cavity, right inside what's supposed to be solid, dependable steel. They're basically tiny pockets of nothing, exactly where you need maximum strength.
So why is a tiny pocket of nothing such a huge deal? Well, it's not just that they weaken the joint. They're way more sinister than that. They create pathways for moisture, which means corrosion can start from the inside out. And worst of all, under stress, a pore is the absolute perfect starting point for a tiny crack to form and then spread.
Okay, so if these killer flaws are totally invisible and buried deep inside solid metal, how do you find them? You can't just look closer. You need a way to see through steel. And to do that, engineers turn to a technology we're all familiar with, just scaled up. Big time.
Yep, the answer is X-rays. Just like the ones at a hospital, industrial X-rays can create a picture of what's going on inside a weld. It's a fantastic way to inspect these critical parts without having to cut the machine open. You can spot pores, cracks, and all sorts of other problems that are completely hidden from view.
But, and this is a big but, there's a catch. The X-ray images themselves, they're often a real mess. They can have uneven lighting, tons of visual noise or static, and really low contrast. A dangerous pore might show up as nothing more than a faint, blurry smudge. It's so easy to miss, even for a highly trained expert.
This is where our hero, the digital detective, finally enters the scene. To fix this problem of messy, unreliable images, researchers developed a really sophisticated image processing algorithm. Think of it like a digital cleanup crew, specifically designed to cut through all that noise and make these hidden flaws just pop right off the screen.
So, how does this thing actually work? It's a super clever 5-step process. First, it converts the image to simple black and white, so it's only dealing with light and dark. Then, it applies special filters to clean up all that visual static. It's kind of like digital dust and scratch removal for X-rays. The third step is pure genius. It creates a high-contrast, black and white stencil of the image, which makes any potential flaw stand out bright and clear. Fourth, an algorithm goes in and traces the exact outline of every single one of those shapes. And finally, the system analyzes those outlines to measure their precise size. It's a brilliant way to turn a fuzzy gray photo into a clear, precise map of potential dangers.
Of course, an algorithm is only as good as its results. The real question is it accurate? I mean, can it actually compete with a human expert who's been doing this for years? To find out, the researchers put it to the ultimate test, a direct, head-to-head comparison with certified professionals.
The results? They were pretty stunning. First up, precision. You can think of this as the don't cry wolf score. And at over 97%, it means that when the algorithm flagged something as a flaw, it was right almost every single time. That's an incredibly low rate of false alarms.
Then there's recall. This is all about not missing anything. How many of the actual defects did it manage to find? The system scored over 98%. It's like a bloodhound that basically never loses the trail. It finds nearly every single flaw that's actually there. And finally, you have the F1 score. This is just a neat way of combining both of those numbers into one. It shows the balance between being precise and being thorough. And a score of nearly 98%, that shows a near-perfect performance. It's both accurate and comprehensive.
But it's not just about finding the flaws. It's also about knowing how big they are. And when you put the algorithm's measurements side by side with the experts, they are remarkably close. I mean, we're talking about differences of just a few percentage points on things that are already microscopic. That is incredible.
In fact, the final analysis showed that the measurement errors were consistently less than 1/10 of a square millimeter. That is just an astonishing level of precision. It gives engineers data they can really, truly trust.
So, what's the big picture here? What does this all mean? Well, this goes way beyond just a cool piece of software. This kind of digital precision has a huge, real-world impact on safety and reliability for all of us.
And here is maybe the most important takeaway of all. The algorithm was sometimes able to spot defects that the certified human experts had initially missed. Now, this isn't about replacing people. It's about giving them a better tool, a powerful safety net to catch the things a human eye might miss, especially after staring at fuzzy gray images for hours on end. And of course, the potential here goes far beyond tractors and harvesters. You can use this exact same technology to make cars more reliable, buildings and bridges stronger, and even raise the already sky-high safety standards in the aerospace industry. This is about a whole new level of quality control, everywhere.
It really gets you thinking, doesn't it? We've just figured out a way to find invisible bubbles hiding inside solid steel. So, what's next? What other hidden, microscopic dangers in our machines, our buildings, or who knows where else are we on the verge of finally being able to see?